In this video, we'll begin Chapter 7. We'll move into Section 7.1 specifically and start discussing integration by parts, but first just a quick overview of what we're getting ourselves into. Chapter 7 is basically about higher level integration techniques. What I have outlined right here are the 6 sections that we're going to go through, and that will be on our next test. And as we go through these, section 7.1, integration by parts, 7.2, trig integrals, 7.3, trig substitutions, 7.4, partial fractions. These are kind of introducing new techniques to us. 7.2, we might say we're expanding on some techniques we learned from Calc 1. But these are new techniques. And then 7.5 is kind of a general strategy. When we start seeing all these problems mixed together, how do we decide what technique works best or what technique has a chance to work? And then we'll very, very quickly mention 7.6. Our book has whole tables of integrals. There's also computer software. This is where if we had access to the computer lab, we'd see how Maple software can solve some of these integrals for us. But in reality, it's these 4 sections. These 4 sections are introducing new techniques, and then one section that'll kind of review and put all those ideas together. So we'll take our time through this, but just trying to point out this is what our next test will cover, and this will only take us a couple of weeks to move through these sections. The next thing I just want to say before we jump in is just to point out integration, while it is entirely based on the concepts of derivatives, and that's how we form so many of our initial antiderivative techniques, but now we have to realize derivatives and antiderivatives are different in the situation that derivatives have very hard, fast rules that we can apply. You see multiplication that you can't multiply, well, you have to use product rule. You see division you can't divide, you have to use quotient rule. Inner, outer setups, that's when we need chain rule. So we have these very hard, fast rules we can follow. Sometimes there might be some problems with a little manipulation, we can make them easier. But again, we always have those hard, concrete rules to go back to. These are not the same. What we will see as we move through these sections, we will have general ideas, when to try and apply these. But all of these, I don't want to compare them too strongly, but they're a little bit similar to U substitutions. U substitutions don't solve the integral for us. All the U substitution does is somehow simplify the integral so that we can solve using traditional techniques. And we're going to see that's kind of what we're going to see here. We'll get into integration by parts in just another minute. There's a formula and some very clear cases where this formula will help us, but we'll get into that in a moment. Trig integrals are literally integrals that just contain the trig functions. So just remembering from Calc 1, the little manipulations and identities in order to take something that we don't know the antiderivative of and convert it to something we do. Really simple. If you thought of the integral of sine squared plus cosine squared, well, individually, they're 2 functions separated by addition, and there's not much we can do with them. You can try use substitutions, but you're not going to get anywhere. But if we apply an identity, sine squared plus cosine squared equals 1, well, now all of a sudden that integral is much more simple, and then we could finish solving on our own. We go through this section in order to get here. Once we know how to handle complicated integrals that just involve trig functions, we're going to then look at a bunch of integrals where we will force trig functions into them. They won't start with trig functions, but we will substitute a trig function in order to apply techniques we learned from 7.2. And then finally, partial fractions will be when we have these divisional problems, and we'll see how kind of the opposite of what we're used to, instead of taking multiple small fractions and combining them into one big one, that's kind of the opposite of what we're trying to do here. We're trying to break these down into smaller, more basic fractions to have easier integrals left with. So again, that's a very, very quick and rough description of where we're going, and each individual section will have plenty of time, plenty of problems. At the end in 7.5, I'm going to give you a nice big list, kind of like what we did with volume, of just mixed problems together so we have more practice and we're very well prepared for our next exam. So Specifically today, we're talking about integration by parts. Integration by parts has this very nice, neat formula right off the bat. It starts off with the integral of u dv equals u times v minus the integral of v du. So, if you haven't seen this, you don't understand how this formula is supposed to work at this point. You will, but just the first thing to point out that this is a little nice in that at least this technique gives us a formula that we try and follow. Little frustrations, we're using the letter u, and we kind of already used to using u for u substitutions, but right off the bat to point out, how we identify u for u substitutions is completely different than how we will set up u for integration by parts. But unfortunately, again, so we're using the same letters. Some people like to start using w and make them w substitutions so that they don't repeat a letter. Again, some people find that necessary. I don't think it's necessary, but just again, be very clear. U substitutions when they're necessary versus a UV situation for integration by parts. The last thing I should have mentioned right off the top at the beginning of this, again, these new integrals that we are going to set up is always about making things more simple. But a part of making things more simple means that we already have a very good, clear understanding of integration up to this point. So that means, going back to chapter 6, all those new functions and u substitutions, those things did not exist in a bubble just for chapter 6. They are going to be coming up in chapter 7. This is a heavy-duty section in that it is already building upon stuff we've already done in chapter 6, not to mention building on ideas developed in Calc 1. Right in the middle of this chapter, 7.3 relies on good work in 7.2. So again, very tough section, but once again, a very good chapter where experience gives us so much of what we need. Where experience, seeing what we've done, and then realizing this is a similar problem to that, so let's try a similar technique. That is a huge way going forward. Because even when we get to the strategy section, it's still not a hard, fast set of rules. It is still very much a hierarchy of, well, you try this, and if this doesn't work, then you try this. And a lot of what you try is based on that identification and what are the things we see. So, still haven't really explained integration by parts, but I'm already going to clue you in. Integration by parts works very nicely in two situations. Number one is when we have a multiplication problem, but just a multiplication problem based on simple functions. So we'll go through several of these, but things like x squared e to the x sine x to the fourth log x. Nothing too fancy. All of them have multiplication, but all of them are, again, pretty straightforward in that multiplication, and there's no inner outer. So when we even think about our traditional techniques to this point, you don't even really have any good possibility for u substitutions. So that's a big situation where integration by parts will apply. A second one would be one simple function, but a simple function with a known derivative and unknown antiderivative. If we knew the antiderivative, we'd be done. So it's a very specific situation. You know the derivative, but you don't know the antiderivative. There's three perfect examples we can say right now. You know the derivative of natural log x, of inverse sine x, and inverse tan x, but you don't know the antiderivative. So I say take the derivative of natural log x, that should be a piece of cake. But if I say solve the integral log x, you don't have that on the f prime side of your f prime chart. So again, that's an unknown antiderivative, but a known derivative. Okay, so there are situations. Here's the formula. Let me continue by giving you a quick proof, and then we'll start applying those ideas. And we'll see these situations, but I'll still give you more clues. Once again, there's nothing set in stone here, but there are some kind of general things we can say as far as how to decide First, when to apply integration by parts, and we kind of mentioned that. And then second, how to identify what is what. But next, let's go through a quick proof. This is actually somewhat related to product rule. But again, I said it at the beginning, there is no product rule for antiderivatives, but this is kind of a result that comes from product rule. Because if we remember our notation, if I'm taking the derivative of a product rule situation, so a u times a v, well, product rule would go u by itself times the derivative of v. So in Calc 1, we often would use a v prime. Here I'm going to use a dv for the derivative of v, plus the original second times the derivative of the first. I should take a quick moment right now and point out the only real flaw with using u and v for the letters here, you have to be very careful that you don't accidentally draw a sloppy v and mistake it for a u. So again, just make sure your u's have a clear tail, whereas your v has a little bit more of the point, so there's no accidental mistakes where we just plug something in the wrong way. Okay, so that's product rule. We've known that for a while now, ever since Calc 1. But now, look what I'm going to do to product rule. I'm going to take the antiderivative of this whole formula, of this whole equation. And just like taking a derivative, this is kind of like implicit derivatives. You don't just take the derivative on one side or the other. You take the derivative on both sides. Here I'm going to apply the antiderivative to both sides. The left side, well, this, again, this is a slightly informal proof, but this is basically applying fundamental theorem of calculus. The integral and the derivative undo each other, so that basically these two things cancel, and we're just left with our plain uv. On the right side, well, realizing I have two separate pieces separated by addition, that allows me to separate that into two separate integrals. And the last thing is just to realize all I've done to take this and get this formula is isolate this integral. Subtract this to the other side, and then just change your order so that this is on the left side, and you get this integral is equal to the original uv minus the integral v du. So again, we still haven't seen how to use this yet, but that's still just a quick proof just to show where this comes from. But when we're done, it's still an integration technique. When everything is all said and done, we'll still have our plus c at the end if it's an indefinite integral, our bar and our bounds if it's a definite integral, and we could still always test all of our work by taking a simple derivative. Okay, so now, still a lot of information, still haven't solved a problem. Let's just get one more little chunk. So this is what you're starting with. If we are going to use integration by parts, we're basically looking at an integral that has one of these two situations, and we're thinking of that integral with this setup. So in order to use this setup, we are going to, from the original integral, assign a value for u and also assign a value for dv. Okay? When we go to continue using that formula, well, notice we'll need a du, so after we assign u, we will take the derivative of u, and that'll be our du. We'll also need the plain original v. Well, we have the derivative of v, so we'll take the antiderivative to get back to plain v. So, I mean, here, right off the bat, there's a lot of little things that bother students when they first see this. Overall, this is an integration technique, but just literally trying to set up this formula, first we have to make two identifications, then we take the derivative of whatever we assigned for u, and then we will take the anti of whatever we assigned for dv. That will be how we finish completing this chart, and that still doesn't finish the problem because we will still have this new integral left to be solved. And the point of this formula If we are first using integration by parts when we should, we have one of these two situations. Second, we've set everything up correctly, then what we should end up with is this new integral in this part of the formula should in some way be better than this integral we started with. Either more simple, more basic, in some way, these problems will somehow be fixed or on the way to being fixed. So again, there's a lot to this, but now back to the identification. How do you pick? Well, again, it's still not set in stone, but we've got a few different possibilities. If you're looking at multiplication of simple functions, you typically try and let u be the piece that will simplify with a derivative. That in some way, when you pick that for your u, and then you go take the derivative of that u, that this piece will in some way be more basic and simple than this piece. A really quick, easy example is something like x cubed. If u is x cubed, du would be 3x squared. And we've kind of seen a little bit, and now we'll get more experience with that. Just having a lower power of x is a better thing. So starting with an x cubed, having a 3x squared, that is a little bit of the simplification I'm talking about. Not simplifying like crossing off common factors, combining like terms, just in some way that the function is more basic than how it started. If you do that choice for u, then dv by default is everything else. But then here's the second catch. Even if you do this basic setup, the dv, whatever else you have here, you must be able to take the antiderivative. So that's kind of the other catch. So we kind of hope u will simplify, but the second possibility is just, if we go to the second possibility, there's only one function here. We know the derivative, we don't know the anti. Well, then that has to be the u, because we know the derivative. So like I said, it's a little confusing, but again, we'll get our practice to try to point out the different things we try and apply. But one thing you cannot do, you cannot go through, do the examples we do here, and even if you do all the examples we do in the video, and then do all the examples in the textbook, you still can't make a definitive list. U is this, dv is that. It never works out that cleanly. Believe me, if it was that clean, I would just tell you right now, you always pick u as the power of x, and dv is the leftover. But that's not always going to work. So again, we have to be flexible. So now let's jump in. Let's jump right into our first problem. All these problems, the directions will be evaluate, solve the integrals. And let's start number one with x e to the minus x dx. So it's only our first example, and for this first one, let's start with this as an indefinite integral. I'm really only going to show you one, maybe two definite integrals. We'll probably just come back and show you a quick little bit at the end, just to show you the plug-in part, the reminder of that. But most of this is going to be indefinite because, again, this is an integration technique. We're focusing on the antiderivative. So, number one. Well, again, we have to evaluate, before we can jump in and start doing any techniques, we have to observe the situation. What are we looking at? X times e to the minus x. There's multiplication. I can't multiply it. And if you ignore the multiplication, I mean, that's really troubling at this stage, everybody. If you just do like an x squared over 2 and then play a little game here, because this is so close to an e to the u, and you get an x squared over 2 times an e to the minus x, again, garbage, everybody. That's just like if you take a derivative here and just say the derivative is 1 times e to the minus x times a minus 1. You would need product rule for that derivative. Ignoring the product situation is a terrible, terrible habit to have at this point. So I have multiplication. I can't clean it up. We're not skipping steps, everybody. I know we're getting into a new technique, so many people just want to jump to integration by parts, but to really be ready for when we get to 7.5, and just in general, you gotta go through the whole process. The basics of, can I just take and solve the integral the way it stands? Okay, if I cannot, are there any quick, nice manipulations that may help me? And the answer to both of those two right now is there's nothing. There's nothing good that helps us. So now moving on, now we'd probably be thinking about u substitutions. And maybe you might try, hey, u is minus x. But it's not. If you try that u substitution, I'll stick it up in the corner here. U is minus x, du is minus 1 dx. You can't get rid of this. And even if you play a little fancy game, you end up with negative u, e to the u, du. You still have basically the same multiplication, and you've just run around in a circle. This u substitution didn't help. So, again, it seems like we've exhausted our options. We tried basics, didn't work. We tried a u substitution, didn't work. Well, now we see this. This is the multiplication of simple functions. Now, if this was e to the x, that would be even more obvious. X can't be any more basic. E to the x, again, it's not the easiest function we've ever dealt with, but it is in its most basic, pure, simple form. And just having an extra negative, or if it was an e to the 4x, that's not enough to throw it off. If this was x e to the x squared, now all of a sudden we've got some real complicated inner outer, and now we go back more to that u substitution. And notice, again, if that was e to the minus x squared, now the derivative would be a minus 2x, and now that u substitution would have worked. But that's not what we had here, so again, that u is not working. So we've got the multiplication of simple functions, so let's try a setup. And now let's just, first things first, let me just pick u as x. Some of us might be thinking, hey, that's super simple when I take its derivative, and you are correct. And then dv, by default, is everything else. And when I say everything else, that includes the dx from the original problem. This, just kind of like u substitutions, it's bad habit to just kind of wave your hands at this. That's a formal part of the notation. It's formally something you substitute in the u substitution, and it's very, very necessary. Dx doesn't just miraculously become du. We got to work to get that to happen, and other good things have to happen along the way. Well, here, it's not quite that bad, and some people kind of get away ignoring it, but it's a terrible habit. So let's have the good habit. dv is everything else, including the dx. So now, if there's my u, du, again, I'm not trying to make this too similar to a u substitution, but just the notation. You move to du by taking the derivative, and here that would be a 1. And it still has to get that marking dx, just like it did for u substitutions. For this part, now I'm taking the antiderivative. And that's a big reason why this is so important. Literally, here to here, you're doing a d over dx. Here to here, you're doing an integral. So some people even set that up on the side. Inside of the integration by parts formula, you're solving this basic integral. And this one would be this. Again, you may need a little u substitution to help you out, but for a lot of us, we can fight our way through it. How do you take a derivative and get this? Well, the derivative of this is the exact same times an extra negative 1. So by putting this extra negative 1, those would combine to give me a positive. But here's the next little thing. If we do this off on the side, good habits, we have the plus c, but just in this notation, we don't need the plus c yet. You'll see why in just a moment. So there is my first setup. And with that setup, remembering the formula, using the formula and now plugging in, this will now equal u times v. So x times negative e to the minus x. I'm just going to kick that negative to the front to make it a little cleaner. Minus the integral v times du. Notice all the little things. Naturally, the antiderivative, the dx, drops here. If you did your proper notation here, now when you set up your new integral, the v du integral, the dx notation comes back into this integral because it's a part of du. So again, everybody, some people kind of like ignore these things and they get some correct answers, but it's just a real poor use of notation. Don't do that. Embrace the notation. Don't try and fight it. So v du minus e to the minus x times 1 dx. The times 1 is not necessary. And now we really get to start to see how integration by parts really works. We set this up, and if we did a good job setting it up, number one, we could complete the box, so to speak. If you have the wrong choice for dv, you can't even get the antiderivative. That's a clear choice. That's a clear sign something is wrong. Maybe you didn't need integration by parts in the first place. Maybe you did a poor choice of setup and identifying what was what. So again, different things can happen along the way. But if you can't even finish the full box here, you're definitely not on the right track. But here should be the better sign. Now, this is a part of my answer. It may seem like it's just done and we're not taking an integral, but we did antiderivative work here to get us to here. But this is really what we're left with. And in some way, this should be better than what we started with. That's how we really know integration by parts is working. That's what's going to allow us to finish the problem. And this goes back to what I said at the beginning. Integration by parts didn't take the full antiderivative. All it did was manipulate the situation so that we're still left with an integral, but left with one we should be able to handle. And I hope you're looking at this saying, yeah, I can handle that. I hope so, because it's literally an integral we just solved a moment ago. That minus can kick out in front, make that a plus. There's your integral e to the minus x. Your final answer would be this. This, still a part of the answer, not to be forgotten about, not to be erased or just ignored, definitely a part of the answer. And then we finish solving this integral, and in total, this whole thing is the answer to this integral. So you want to check your answer, you take the derivative. But again, the derivative of the whole thing. This is what we were saying earlier. If you have this set up correctly, you are going to end up with some product rule here. The formula came through that product rule formula, and there we see some product rule. The derivative here, product rule, minus 1 times this. Actually, let me even just show you quickly, just a quick confirmation. So if I took the derivative of all this, I get minus 1 times the original second, plus the derivative of the second times the original first, and then all that is the derivative here, and then the derivative here, and the derivative of c is 0. And initially you might say, well, wow, that didn't work. But take an extra moment, look at this a little more carefully. This is a minus e to the minus x. This is a plus e to the minus x. And they actually end up canceling. And this middle piece here, after you clean it up, minus 1 times minus x times this, is the exact same thing we started with. So it may have seemed strange because you're getting so much more, but through the nature of the product rule and the other piece, that a little bit will cancel, and that's why this works. So that again, all of this is the antiderivative of this first function. And now, like I said, let's just jump right in and let's see what would happen if this was a definite integral. So if this was, I'm not even going to count this as number 2 because it's really just doing the same thing over again. And let's just keep this fairly simple. Let's just do the integral from 1 to 2, x e to the minus x dx. Well, definite integral or indefinite integral doesn't matter. you're still taking the antiderivative. So, same function, same situation. Again, I didn't jump into integration by parts. I realized the multiplication. I realized there was no quick, easy simplifying. I saw no good choice for U substitution. Then I established it was a good integration by parts problem. We did all of this. So I'm just going to jump to the answer here. And here's the big difference. Just going back here, you don't need 2 plus c's. You don't need a plus c here as a part of v, and then you get another plus c. If you had a plus 1 and then you had a plus 2, well, they could combine to just be a plus 3. So that's why up here we didn't need the 2 plus c's, just 1 at the end was enough. But now as a definite integral, we don't get any plus c's. We get the bar. And the big reason I want to bring this up, the common issue is when people are doing this definite integral and they do integration by parts, they get this, they get the new integral, they put the 1 and the 2, the bound's still on there, they solve this integral, and they think the bounds just apply to this piece. But again, all of this was also a part of the antiderivative generically, so all of this is the antiderivative as far as when we're plugging in. So plugging this in, we would get minus 2 e to the minus 2 minus e to the minus 2. I plugged in the first into everything minus the quantity, and now I'm plugging in the bottom bound. You know, could I clean that up a little bit? Sure, there's a tiny couple little things, nothing too big. I could eventually flip these e's into the denominator, get common denominator. Again, that's not the point here. The point was just to point out, if you're solving a definite integral using integration by parts, that you're plugging these bounds into the whole thing, not just this last piece. All of this is the antiderivative. All of this is the capital F of x that goes with the little f of x here. Last thing before we move into another problem. People go back up here, they saw the integration by parts setup, and they say, well, why is he making such a big deal about the u and the dv? Look, it's obvious. If this is supposed to be u dv, well, look, it all lines up. There's your u, and there the rest is your dv. It's not always going to be so beautiful left to right, everybody. It's not always that perfect. I mean, x times e to the minus x, yeah, that's a good form to write it in, but it could just as easily be written e to the minus x times x. So just because someone wrote it in a less desirable form, well, now that basic u and dv setup is not going to work. So that's one big thing. As I said, there's no hard, fast rules for what is u, what is dv. We have to have experience. We have to try. But make that very clear, that's not a good way. There's a decent number of problems that integration by parts that it does work out that u is the first piece. But again, it's not enough to make that any kind of a rule for us to think about. The second thing, so all this is done correctly, but now let's just realize what happens if you picked your u and dv wrong. What if you thought u should have been the e to the minus x, so then by default dv would be the x dx? I mean, initially, if you're just filling in the rest of the chart, it doesn't seem bad at all. Du, the derivative of u, is itself times an extra 1, and I'll get the dx. The antiderivative of x, well, that's not bad. That's x squared over 2, nothing fancy. So if I apply the formula, u times v, right, u times v, minus the integral v times du. I'll even kick that extra negative out in front just to make this a little cleaner. And there are people who would say, hey, I did it correctly, but you're missing the big picture. Getting this set up is nice, but that's where it's here. This is what really determines if this integration by parts setup was working. Is this in some way better? And in this one, we saw, yes, it clearly was. Before we had multiplication, and now there's no multiplication. We went from two functions being multiplied to one pretty basic function. That was big progress. We could finish this integral on our own. But when you get to here, it's worse. You're still in the same situation you were up here. You still have multiplication, but things have gotten worse. X was not great, but x squared is worse. That didn't get more simple, and that's what I was saying. That's why I don't want us to be so focused on the word simplify, like things we're going to cancel, but just this is definitely more complicated because it's a higher exponent. So that doesn't tell me my integration by parts failed. It just tells me my choices for u and dv failed. Okay, so we've said a lot in this first part. Let's take a pause and let's move into a second part, and the rest will just be practice, more problems for us to go through.